Hello. So I hope you're doing very well and we prepare to finish this course. Just 2 more weeks to go. Okay, so what we are going to do is we are going to have the quiz. You know that your last quiz is going to be on Monday next week. So I will post a practice quiz for you. Okay, then over the weekend that I post the quiz, you know that the quiz is going to be just as you did it before. You did it yourself, and then you go back and you you submit it into the canvas, and there are going to be assignments. I already posted the assignment for you. It's going to be up to the section 5.4. It's a very brief application of a differential equation. So what we are going to do, we are going to hope to cover kind of 3 sections of chapter 6. Chapter 6 is quite interesting. Let's talk about the inner product space. Okay, if you want to continue, see the application of a combination of application of the linear algebra and whatever concept that you do in calculus. The combination of these two, you need that inner product space, chapter 6. So if you want to do something related to the concept of the calculus, you see, or in mathematics, you should be able to identify or to define the distance. You see, when talk about continuity of the function, for example, in calculus, we say that f is continuous at the point A if the limit of f of x goes to A would be f of A. So in order to talk about x going to the A, you have to know what is going to be the difference between x and A. So the difference would be defined by an absolute value, which is going to be kind of distance between two numbers. So if you want to do the same thing in we do it in calculus 3 in 3-dimensional, and we introduce the vectors rather than the point, and we define their distances. So now that you are familiar with the vector space, so how about defining this concept, the concepts of a distance between two vectors, two members of the vector space, but in a general abstract vector space. So as soon as you identify the distance, then what you can do is, okay, the distance in ordinary case is absolute value, but in the case of the vector spaces, you remember we did it for the Euclidean space, we can bring the notion of the R, notion of the norm, and just do it. So you have a vector space and you want to be able to bring a new machine equipped to your vector space with the distance formula. And this is where you are going to bring the inner product. Okay, remember we already talked about the dot product. Dot product on the Euclidean space and be related to the norm and give you most of the property in geometry. We proved it in terms of the norm in Rn. That was a very special one. So what we are going to do is we are going to give you an extension of that idea of the inner product space on the Rn. But this time we do it in a general vector space. So sometimes you may not like to work with the vector space Rn. You may like work with the vector space of continuous function, integrable function, matrices, polynomials. So how are we going to define the distance between two members? Okay, so it's quite interesting subjects or the topics, and that this is where you are going to use this type of ideas in advanced level. So you will like it and you will enjoy it really. So we just give you a brief interpretations introduction, and I give you the hint of where this concept would end up. Okay, you'll be surprised to see where is going to be the end of these problems. So we are going to take this section slowly. So tonight I will cover the definition just of the inner product space, and we give a couple of questions on the quiz so that you get to know them, and then it's going to be getting better We try to give you as much as we can, but I'm not going to go over more than 3 sections, okay? So this is going to be a 6.1, and we want to know what is inner, okay? This is it, what is going to be inner product spaces. Product spaces. We are going to deal with the, okay, we are going to deal with the complex, deal with some scalars. So sometimes we refer to it as a real inner product space, but I'm going to tell you what will happen for these numbers. Okay, so just recall that what we did with that, okay, with that dot product. Okay, so recall that. Okay, recall that if, okay, if let's say x and v or u and v, okay, u and v are going to be vectors, okay, vectors in Rn, okay, then remember the dot product. The dot product of u and v is going to be defined by, remember it's going to be defined by what? It's going to be u dot v. Remember we define it to be something like, let's say ui vi, which is going to be u1 v1 plus u2 v2 up to the un vn. Okay, that's going to be the one. And you know that this is where I just take it into the dimensional. This is where, okay, where u is going to be equal to the vector u1, u2 up to the un. Okay, that's going to be your u. And v is equal to v1, v2 up to the v. Okay, so that was the one that I call it the inner product. So what we did is we picked two vectors and we assign a number. You see, u dot v is going to be just a number. And quickly, also, we did this have these properties, okay? We know that this is going to be just a number. So the first thing that we did was, for example, this is going to be commutative, if you like, or symmetric. U dot v equal to the v dot u, because these are just a number, you can switch it. Okay, and the other thing was if you want to multiply by a number, okay, this one, if you just let the u and the v to be equal, let's go with the, okay, no, for example, if you have a u plus w, okay, times dot v, you can distribute it, remember? That was a kind of a linear, okay, and this is it. And then the other one was if you have a constant k, remember if you want to have a k times the dot product over here, so that was k v dot v, and k is just a scalar, let's say is a real number, real scalar. The complex one, we are going to do it later on. Okay, so the other property was we know that u dot v, u dot u would be what? This is going to be just the square of the u1 square, u2 square, etc. So this is always greater than equal to the 0. And in fact, u dot v is equal to the 0 if and only if u is equal to the 0. Okay, so these are the property that you did, okay, we can easily see that's going to be true for Rn. Now, then we continued, we just call u dot v. Remember u dot v, we call it norm of u squared, and then we continue getting a various property, okay, a property of the norm, if you like, okay. Just remind you that what we did is in this case we just define the norm of the u, if you like. The norm of the u is going to be u dot u to the half, or the square root, which is going to be the square root of u1 squared, u2 squared, up to the un squared. This is what we did. Okay, we introduced the norm, and just we take it from here. So as soon as we defined the norm, we were able to define what? We were able to find the distance, okay? So the distance between two vectors, we define the distance to this vector to be just a norm of u minus v. So we were able to define the distance, and then we were able to define orthogonality. Remember, u is orthogonal to the v if and only if u dot v is equal to the zero. Okay, so by simply defining this inner product, we were able to take care of everything for us. We define the norm. As soon as we define the norm, we can define the distance. And if you want to go to the calculus, the notion of the continuity, limits, etc., you just need this distance over here. And then orthogonality was very important for us, okay, to get the various properties. So this is what you know. But you know it for this very standard, okay, you know it for a very standard space. This Rn, and these ideas that we put over here, together we call it Euclidean, okay, space. We call it n-dimensional Euclidean space, because all the property of the geometry can be extended. Now, what we are going to do is we are going to start it over. So this is Rn. Replace it by anything you like. Okay, replace it by anything you like. So let's have a vector space. Okay, so we are going to switch. Okay, we are going to switch to this one. Now, suppose you just give me something in German. So this is going to be the one. Suppose. Okay, this is it. Suppose V is going to be a vector space. The scalars that we're going to use are going to be important. In the case of the complex numbers, is going to be a little bit different. So we are going to focus on the real scalars only, okay? So we say suppose V is a real. Okay, so every vector space that I'm going to use is going to be real vector space, means I'm going to use only real scalars. So suppose V is a real vector space, anything you like. Okay, it's going to be real vector space. So I change the Rn into the V. Okay, so what I would like to do, I would like to define something like the inner product. So what is the inner product? I have to pick two vectors u and the v, two vectors u and the v in the vector space, and I have to assign a number to it. Okay, I have to assign a number. So assign a number to it means I have to introduce a function. Okay, so this is going to be a real vector space. So what I'm going to do is I'm going to pick, you see, I'm going to pick a pair of the point. A pair of the point means, you know, pair of the vectors. So I pick a pair of the vectors in, okay, a pair of the vectors, u and the v. Okay, this is going to be a pair of the vectors. So I would like to drop it into the function. Okay, this is going to be a function that I'm going to be interested in. Okay, this is a function that I'm going to introduce in. So I'm going to call this function, okay, it doesn't matter, I'm going to change it in a minute. So I'm going to call this function f. Okay, so the result is going to be f of u and the v that I pick over here. Okay, so I want the result to be a number. Okay, so I assign a number to it. But this function must satisfy these four conditions that I put over here. Okay, because I want to replace dot. Anytime you see the dot here, I change it to the okay, inner product, I call it. So what we're going to do, suppose V is going to be a real vector space, and suppose we have a function. So we have a function from what? The function is going to be from order pairs in V. So it's going to be V cross V. Okay, V cross V means order pair of the vectors in V. This function should be defined to the, okay, into the real number. real number that satisfy this condition. We have a special notation for this function, okay? Instead of this dot, dot, dot that we use over there, we're going to use this notation, okay? The notation of the U and the V. You can use even the parentheses, but I go with your book. Okay, this notation over here, we are going to call it, okay, we call it inner product. Okay, this notation is going to be our inner product. Okay, this is inner, okay, inner product. So, which is going to be a function, okay, which is going to be a function, but this function that satisfies this condition that we talk about it. Okay, suppose V is going to be a real vector space, real vector space. Now, an inner product, okay, this is going to be the case, and inner product, okay, and inner product on this vector space on V is going to be a function. Okay, it's going to be a function. What is that function from? V cross V into the R. Okay, so we just define it that we get a pair of point, assign it to a number. That number would be denoted by, okay, U and V here. Okay, an inner product on V is a function that assign or that relates, okay, relates each pair of vectors U and V to a number, to a real number, That real number will be denoted by U V in this format. Okay, so it's going to be a function that take a pair of the vectors and related to the R. This is going to be number R. Okay, relate each pair of the vectors U and the V to a real number U and V, satisfying the following. Okay, satisfying the following condition, if you like. Okay, satisfying the following. Now, the following are going to be exactly the one that I did over here. Okay, so check the condition as we did it over there. So the first condition is that say it must be symmetric. Okay, so this is going to be the first condition. Okay, so the first condition is the first one. The first one is symmetric condition. This means the inner product of U and V must be the same as the inner product of V and U. Okay, so this is symmetric property. It's like looking into the mirror. This is the first property as we did it over here. Okay, so we take care of the first property. The next property is just that linearity that we talk about it. Okay, that is the case that what is the linear one? It's going to be linear on the first component, if you like. So instead of the you may have U plus W. If you have U plus W and V, you can distribute it. You can distribute into what is going to be U comma V, the inner product, plus, okay, plus W comma V. Okay, so that is, we extend the second one. The third one, a scalar multiplication that we have. So the scalar multiplication will be if you give me a K, and if you want to multiply the K by U and V, okay? So what you can do is you can take the K inside if you like, or pull it out. It's going to be K U, okay? So that is going to be K U V. Okay, this is going to be the condition that we have. So K is a real number, is a real scalar. Okay, so that would be the real scalar that we're going to have. Okay, and what is the last one? Okay, so the last one is, it must be, if we consider, the u comma u, inner product of the u times u, if you like, this must be always greater than or equal to the zero. Okay, it must be greater than or equal to the zero. And if this is going to be equal to the zero, okay, it's going to be equal to the zero if and only if the vector u be just zero vector. Okay, so exactly the condition that we talk about it are going to be satisfying over here. Okay, that's exactly the condition that you did have for the, okay, you did have for the, for your inner product before. Okay, so if you can define, such a function with this property, so this is going to be, okay, so this is going to be an inner product. So in this case, you see, if you define an inner product, so in this case, okay, in this case, V is going to be called, okay, V is called a real, okay, real inner product, space. Okay, so if you have a vector space with an extra machine, that extra machine is going to be a inner product function, if you like, or the product. You see that this space is going to be a real, okay, just inner product space. Okay, so you have a new tools in your vector space. Okay, so let's quickly get some example. So the previous one that we did have, so the example that we can have to this property, the first one is just the one that we did. Okay, if V is going to be equal to the Rn, okay, Rn with the standard inner product, with the standard, okay, standard dot product, if you like, dot product. So this is going to be the case. So and then you see, if you define the inner product to be, so you can define your inner product u and the v to be exactly the same as the dot product. Okay, define it as a dot product, and you know the dot product is going to be u1 v1 u2 v2 up to the, okay, up to the what, un vn. If this is going to be the case, then you can consider that the Rn is going to be, is an inner product space. Okay, inner product space. But you may have various, you see, now we have a chance. We can have various, okay, different, if you like, inner product in Rn. This is the one that we call it a standard. So with this standard one, we refer to it as a Euclidean, okay, Euclidean space, if you like. And this is where, you know, you define the Euclidean geometry. So in Euclidean geometry, the distance is going to be just, you know, the usual standard distance. But in a minute, you will see that I can define various type of inner product on Rn. So that gives us a chance to study the so-called non-Euclidean geometry. So there is not going to be a restriction on our, okay, on our procedure, if you like, to get these numbers. Okay, so let's give you some unusual inner product that we're going to have. So this is going to be the first one. Now it's very easy to create a more inner product on the Rn. You see, these are the one. So we can multiply each of these terms by a number. We call it a weight. Okay, so multiply this one by 4, 5, 6, 7, etc. Then they give you a new inner product. So you have several of these in your book, and they may ask you to identify it. So let's try one of them so that you know that how we're going to do the problems, and we may give you one of them on the quiz. Okay, So just we check one and then we write a general one for you. So I'm going to do it in R2 and then we can do it, in various format. Okay, so one case in R2, I just can use this one. Okay, so the other case is going to be, okay, so suppose, for example, I'm going to show that V equal to the R2 with a different inner product is going to be, with a different definition, is going to be inner product space. Okay, so for example, let U to be equal to, let's say, X1 and X2. Okay, this is going to be the one, and the V equal to, let's say, Y1 and Y2, and W, for example, W is equal to Z1 and Z2. You can use different notation for this. Okay, this is going to be the one. So these are going to be just vectors. Okay, these are going to be vectors in R2. Okay, vector in R2. So what we would like you to do is, we would like you to prove that. Okay, we would like you to prove one of those weighted definition. Prove that if this inner product U comma V, okay, defines, if this is going to be defined as follows, okay, as follows, is an inner product, okay, it's going to be inner product in or on R2. Okay, and the definition is, you have quite a lot in your assignments. So the definition is that they define the inner product of U comma V. They change it to those ordinary one. For example, this is going to be, X1, Y1 plus 4 times X2, Y2. Okay, this, they call this one a weight. You see the coefficient of the first one is 1, the other one is 4. It doesn't matter. You can use various numbers, and at the end of the day, you are going to have, okay, you are going to have a inner product, and they ask you sometimes to find one of them. Okay, so then they ask, determine the inner product, determine the inner product of the vectors. Okay, inner product of the vectors. They give you two vectors. The vectors are -2, 5. Okay, and 3 and 1. Okay, 3, 1, 1. And there, of course, and there, okay, this inner product, this inner product. If it's going to be a standard one, we know that just the dot product is standard one. But you want to do it with this case. Okay, so they are not going to be difficult to prove. It's going to be a little bit messy because you have to check all the conditions that we talk about it. Okay, you have to prove those 4 conditions for us. So the solution is going to be, you go with the first condition, which is going to be okay, to axiom 1, we call it the symmetric one. So you start with the U and the V, and then you switch it. Okay, so I have the U and the V. I want to prove that this is going to be equal to the V and U. It's easy because they are numbers. Okay, so you say that this is X1, Y1 plus 4X2, Y2. So easily I can switch it into the Y1, X1 plus 4, okay, Y2, X2. And according to this definition that I have, so this is going to be what? This is going to be simply V times U. So I prove the first condition. The first condition is that it is symmetric. Okay, so it's a kind of, they compute and you get your numbers right away. Okay, so you have to show it, and then you ask you one of these questions on on the quiz and of course on the final. Okay, so that's the first condition. The second condition is that linearity that you have to prove. Okay, so you have to pick three vectors to prove it's going to be linear. So what I do is I'm going to, you have to prove that it's going to be linear on the first component. So I pick something like u plus v and the w, and I am going to expand it. Okay, so this is it. So let's form the u and the v that we have. Okay, remember the u was x1, y1, and the v was x2, y2. So this is going to be equal to, okay, simplified a little bit. So the first vector is x1. Okay, this is x1 comma x2 plus y1 comma y2. Okay, that's going to be the one. And this is going to be the first component. So the second component is w, the one that we call it z1 comma z2. Okay, so this is what you have. Simplify this one a little bit. So you know that it's just ordinary addition. So it's going to be x1 plus y1 comma x2 plus y2. Okay, this is going to be your, this is, okay, you add them together. This is going to be the new one. And then you have the z1 comma z2. Now we can use the definition of your inner product. So remember the definition of this inner product is x1 y1. You multiply these. Okay, that was the definition that we have. You see x1 y1 plus 4 times x2 y2. So this is going to be the one. So your x1 is going to be x1 plus y1. Okay, so it's going to be x1 plus y1, the first component, times z1. Okay, plus 4 times x2 plus y2 times z2. Okay, just distribute it, put them together to get the new inner product. So it's going to be equal to the what is going to be x1 z1 plus y1 z1, and this is going to be 4 x2 plus okay, so this is it. So it's going to be 4 x2 z2, okay, and 4 y2 z2. Remember what you want to prove. You want to prove that this is equal to the uv and the vw. Okay, uw and the vw. So put them nicely together. Okay, so you have the x1 z1 plus 4 x2 z2. Okay, so that will give you uw, and if you get the other one, y1 z1 plus 4 y2 z2, so that gives you exactly the definition of the second one. So this is going to be the inner product of the u and the w. Okay, and the other one would be the inner product of the v and the w. Okay, so you prove that this is going to be linear on the first component. Okay, so u plus v comma w is the same as the uw and plus vw. Okay, so you prove the second axiom, we call it linearity, or you know, it's additive. Okay, so we have to check the third condition. The third condition is easy, a scalar one. Okay, so the third condition is going to be, you go with the k times, see, this is it. You check the k u comma v, and you want to prove that this is going to be k times uv. So we have to go with the definition that we have. Okay, so this is going to be equal to kv is going to be k times, okay, this is x1 comma x2, and the other one is y1 comma y2. Okay, and this is just a scalar multiplication of a vector, so they make it into the kx1 comma kx2. Okay, this is going to be the case, and you have the y1 comma y2. Now we can use the definition of the scalar product. The scalar product, remember, it's going to be x1 y1, so this is going to be k x1 times y1 plus 4 times, okay, k x2 y2. So if you factor out the k, that give you x1 y1 plus 4 x2 y2, which is exactly the inner product. So it's going to be k times the inner product of the u comma v. So we proved it, that they call it homogeneous one. So if you have the scalar on the first component, you can pull it out. So this is going to be, you know, the third condition that we did have. Okay. And so there is one more to prove. And the one that, you know, if you, the inner product of one vector by itself is going to be non-negative. So we get to the fourth one. So in the case of the fourth one, we have to form a u multiply by a u, if you like. Okay, we go with the definition that we're going to have. Okay, and so this is going to be simply true, really, because this is it. This is x1, y1, and the x2, y2. Okay, so it's going to be the first component that give you, sorry, x1, x1. So that simply give you x1 squared. Okay, x1 squared plus 4y1 squared. They are just a real number, so the square of these numbers are going to be non-negative, so this is going to be greater than or equal to the 0. So you prove that the inner product of the u times u is going to be greater than or equal to the 0. Okay, and one more. The other one is that if you let it to be equal to the 0, okay? So if this is going to be equal to the 0, so this means x1 squared plus 4y1 squared must be 0. And you know that this is sum of two squares of the real numbers. So this means you should have the x1, okay, must be 0, and the y1 must be 0. So this will tell you that the u is a 0 vector. And just coming back. Okay, and so that's it. So you prove that this is it, the uv. Okay, uv is equal to the 0 if and only if u is equal to the 0. Okay, so what we did is we defined that this definition is going to be an inner product. Okay, so R2 is going to be an inner product. Okay, inner product space with this new one. Okay, they call it weighted inner product. It doesn't matter. Okay, it's like the original one. If you multiply any number you like, it doesn't matter. You get the result. You have quite a lot in your book. You see, we call it a weighted inner product. So in general, if you like, I can write it down. Okay, so you know that this is going to be the expression that it is in your book. So we just want to make sure that you don't, get familiar with this notation. Okay, so in general, okay, so this is going to be the case. Okay, we give you a remark of this definition. Oh, I did have something else too. They usually ask to test it. You see, they want you to find, okay, find the product of these two numbers. So you have to do it. So we're not done. So we want to know what's the product of, okay, so what was the number? So you want to find the product of the, okay, so this is it. So you want to find the product of the first vector. It was negative 2n. Okay, negative 2 comma 5. This is one vector, and the other vector is going to be 3 comma 1. Okay, they ask for this one. You know that the result was what? X1 y1 plus 4 x2 y2. So you just multiply them together. This is going to be the result. X1 y1 is going to be negative 2 times 3. Okay, plus 5 times, okay, 5 times 1. So that gives you a negative 6 plus 20. The result is going to be equal to the 14. Okay, so for with this product, okay, the product of these two vectors are going to be, okay, this is it, is equal to the 14. So we're just introducing, a new format. It's not going to be the Euclidean one that we used to it. So they call it a weighted, okay, the weighted product. So in journal, all your assignment, they just change that numbers that you are going to have, okay. In general, if you have, okay, pick some numbers, you call it weights. If W1, W2, up to the Wn are just positive numbers, are positive, okay, they are going to be positive numbers, okay, positive numbers, and if positive numbers, and if, okay, we get the U to be equal to U1, U2 up to the UN, okay, and V is equal to two vectors, okay, V1, V2, or XYZ. The Vn, okay, this is going to be the case. Then, okay, then U dot V, or the product. If you define this inner product to be, okay, just a number, W1 times U1 V1 plus W2 times U2 V2 up to the, okay, Wn times UN Vn. Okay, the thing that we did on the top, it can be, okay, can be done. Okay, this is going to be is an inner product. Okay, it's going to be an inner product on Rn, okay, or Rn, and it's going to be called, and is called, okay, it's going to be called the weighted, if you like, the weighted. Okay, it's going to be called, this is it, weighted, okay, Euclidean, weighted inner product, or just weighted Euclidean, okay, inner product, inner, okay, inner product, with weights, with weights W1, W2 up to the Wn. Okay, so if you, unless you've been asked to prove, we ask you to prove something else, but in case you've been asked to prove, that's a proof that I gave you, but otherwise you can consider this one as an inner product right away, okay? You don't have to be worried about it. But there are some problems that they may ask you to prove it. So then you are, okay, you are ready for it. So this would be, sorry, this would be a class of the very popular inner product that you are going to be, you should be familiar with, okay? So the other example that we have is the example with the matrices, Okay, so let's define something. What is going to be the standard inner product that we can define for the two matrices? I give you one example, then I change it into the a general formula, a couple of expressions. But then if you be given matrices, so you should be ready for it to give us, you should know that this is the inner product that can be defined on the matrices. Okay, so this is it. Let's do one example, then we extend it. We usually go with a 2 by 2. So consider the next example. Consider the vector space of all 2 by 2 matrices. Okay, this is it, vector space. Okay, vector space, M 2 by 2. Okay, is going to vector space of all. Okay, of all 2 by 2 matrices. Okay, you know that we do ordinary operation, a scalar multiplication, and the vector addition. This is the vector space. Okay, now we are going to define a product for you. Okay, this is going to be the product. Let again U and V. Okay, U and V are going to be, okay, U and V are, be defined, okay, as follows. So they are going to be 2 by 2 vectors. Okay, so the first one is U equal to the A, B, C, D. Okay, that's the first one. And the second one is going to be E, F. Okay, E, F, and the G, H. Okay, this is going to be the definition of your vectors that we have it over here. Okay, now in order to remember this product, we use this notation. So this is going to be defined as follows. We want to show that or prove. Okay, we want to prove that the following. Okay, prove that the following function. The following function is an inner product. An inner product. Okay, it's going to be an inner product on M 2 by 2 if you like, or just 2, 2. Now, what is going to be this definition that we're going to have? Okay, I write the definition, then I explain it for you. What does it mean? So we are going to define the U dot V, if you like. The inner product is going to be equal to the trace. I'm going to explain it. The trace of the U times V. Okay, I just double check it. Okay, it's going to be U times V transpose. Okay, the formula would be given to you in this format. Okay, or the U transpose V, it doesn't matter. Okay, this is it. It's going to be the trace of the U transpose. Okay, U transpose V as a matrix. Okay, I rewrite it so that you know. Have a, let me just go to the next page and explain it for you. Okay, so we defined the inner product to be equal to the trace. Okay, trace of the U transpose. Okay, U transpose times V, or the other way around. Now let's see what does it mean. You see, they are going to be matrices. The trace of the matrix is going to be the sum of the terms on the main diagonal. The trace, the trace of a matrix, the trace of a matrix A, for example, is going to be the sum of everything on the main diagonal. See 1, 1, 2 up to the n if you like. This is going to be the definition of the trace. But if you want to see it in this case, you see U transpose V or the other way around. So for example, if you have the U transpose, what is going to be U transpose? Remember, this is going to be U, the transpose, you just switch the row and the column, okay? So the U transpose is going to be A, B, okay, A, B, and the C, D, that's the U transpose. Then you multiply by the V. So the V that you have is E, F, okay, G, H. Okay, that's going to be the one. So if you multiply them together, okay, if you multiply them together, the result is going to be what? Cross multiply is going to be A, okay, AE is going to be AE plus CG. And over here is going to be AF plus CH. And over here is going to be BE, okay, BE plus DG, okay, DG, and the last one here is going to be, okay, it's going to be BF, going to be BF plus DH. Now the trace of this matrix, okay, so that is, sorry, that's U transpose times V, okay, U transpose times V. Now what's going to be the trace? Okay, the trace is going to be just the sum on the sum of the numbers on the main diagonal. So that's going to be AE, okay, plus CG, CG plus, okay, plus BF plus DH. Okay, so that gives you the definition of the inner product, okay, AE and the CG and the BF and the DH. In some books, they don't use the notation of the trace, and they give you this formula right away. But it would be easier to remember it, okay, in this format. Okay, so this is the one we call it a standard. Okay, we call it a standard inner product. So we want to prove that the following is going to be an inner product on the okay, is going to be on 2, 2. It's not difficult to prove. Okay, it's going to be just messy, you know, just substituting these numbers quickly. We can get it. You see, this is going to be your formula, and you can substitute. Okay, I can show you just one of those properties. You see, the first property is very easy. The first property is that you are going to consider the U and the V. Okay, and you want to switch it. It's easy to switch because this number can be switched easily. Okay, I just write it down and we accept it. It takes times. So this is going to be true because just switch these numbers. The second one is if you just okay, so we switch these numbers quickly, we get this one. The second one is just the linearity. Again, it's easy to find. Okay, so this is going to be true. Okay, B and the W and the V, and the other one as well. Okay, so you know it satisfies easily. If you have the KUV, it's just going to be a number involved. So it's going to be KUV. And the last one is clear that this is always greater than or equal to this. Okay. So from now on, anytime you use it, we accept it. But you must be aware of this formula for the test or for the problems. So we are going to call this one. Okay. So we say that the vector space. Okay. The vector space, let's say M2 by 2 is going to be an inner product space. Okay, inner product space. Okay, so be ready for it. Okay, to apply this one. So for example, if you want to multiply two matrices, with this condition. Okay, so note that, for example, if you want to multiply with this one, so if, for example, if u is equal to a matrix of a 2, you have some in your assignment that they ask you to do it. If this is going to be the u and the v is going to be the other one, so it's going to be 5, 2, then 9, 0. You can find the inner product right away. You can memorize the formula or just do it. Okay, maybe doing it would be easier really to memorize that formula. Okay, so if this is going to be the case, then you may be given one to find. So the product is going to be equal to, I go with the with the trace formula. So this is going to be the trace of, the trace of the u transpose times v, or just apply the formula if you like, or just format. So this is going to be the trace of the product of the u transpose. Okay, u transpose, just switch the row and the column. 2, negative 3, 0, 1. Okay, this is going to be times, you times it by the 5, 2, 9, 0, and you add the 1 on the main diagonal. Okay, so it's going to be trace of, so what's going to be the result? It's going to be 2 times 5, 10, so that gives you 10. And over here, this is going to be 4. Okay, if you multiply this one, negative 15, and 9. Okay, so that gives you a negative 6. And if you multiply this, negative 3, 2, 6. Okay, that give you 6. So if you get the trace of this matrix, you must get the numbers. Okay, I'll just check it again. So that's a 2, negative 3, 0, 1, and I have the 5, 2, 9, 0. So what I did, I switch it first. So it's a 2, negative 3, and the 0, 1, and the 5 times. So if I multiply, that give me 10. So I multiply this one, that give me 4. And this is going to be negative 15. And the 9, which is going to be negative 6. And this is going to be just, this is the one I missed. It's going to be negative 6. Okay, this is going to be negative 6. Okay, negative 6. Now the product, the trace is going to be the sum of the main diagonals. It's going to be 10 plus negative 6, which is equal to 4. So the product of these two vectors, u dot v, is equal to 4. Okay, so make a note. You should know the formula. Okay, so if they've given an example of the, from time to time, there are other characteristics of this space that we want to investigate. So we must know the product. Okay, so this is a second example that we're going to have. And the other examples are going to be with the functions. Okay, how we're going to define inner product for the functions. The famous one that we use is integrable functions. Okay, it's going to be functions or polynomials. It doesn't matter. Okay, so you must know this space, the linear space of all continuous or just integrable function. So this is going to be the next example. Okay, next example. Suppose you are going to consider. Suppose V is, this is the way we write it down in your book. They write a C of closed interval of A and B. So this means the space of all continuous is going to be the vector space, integrable or continuous. If this is going to be the vector space, vector space of all continuous, continuous functions. real functions. Functions on a closed interval are A and B. Okay, so it's going to be famous vector space. You must know that the standard product that we're going to define is going to be this one. Okay, this is going to be the case then. So if you have two functions, if f and g are going to be in the vector space V, then we can define the product. If you define this one as, okay, you can define it as an integral from A to B. Okay, integral from A to B, f of x times g of x. Okay, g of x, then the dx. Okay, so we define the product to be the integral of the product. Then we can show that easily that this is going to be an inner product. Okay, then V is going to be an inner product space, an inner product, okay, product space. It's very easy to see. You see, because it's integral, so it's easily seen that, you see, if you switch it, nothing would change really. That's one. Because you see the product, because you integrate f of x times g of x, it's going to be the same as, you know, integrating g of x times f of x. So it's going to be the same. And the linearity is again true. So if you have something like, let's say f plus h function and the g, you see, you know that the definition would be integral from a to b, f of x plus h of x times g of x dx. And you know it from calculus that the integral is going to be, okay, linear. You can multiply the gx and then expand it. So it's going to be a to b, okay, f of x, g of x, d of x plus integral from a to b, okay, h of x times g of x, d of x. Okay, so the first one is going to be the product of f and g, and the second one is going to be product of h and g. So the second condition satisfies easily. Okay, and the third condition is going to be obvious. Okay, the third condition means if you have a constant, you know that you can pull out the constant out of the integral. So it's going to be k, f, and g. And the last condition is going to be that if you have the product of f and f, it's going to be integral from a to b. It's going to be f of x times f of x dx, which is integral from a to b, f of x, okay, squared, which is bigger than or equal to the 0. So it's easily seen that this is going to be an, okay, this is going to be an inner product space, if you like. So that give you the hint really that you just extended that idea. Okay, so this is going to be what we call it romantic space really, because you have an abstract space and it can contain anything you like. So you can use in different form, okay, and that will help you because not all the phenomena, you know, would be satisfying, if you like, the usual Euclidean geometry, if you like. So you may need a new tools. So this is the way you are going to use your tools with the inner product. Okay, so what we did so far is we just introducing the inner product, but what was the idea? The idea is we want to be able to bring those, we call it topological properties, the properties that are dealing with the limits and continuity. So as soon as, remember, as soon as we talk about the dot product, we were able to define the norm of the vector. Okay, so there you are, we are ready for it. So if you have a inner product space, we can easily define the norm. How are we going to define the norm? Norm is a number, remember? So look at this one. This is exactly what we did before. This is going to be a positive number or a non-negative number. Since it's a non-negative number, so what we can do is we take the square root of this and we call it the norm of the vector. Okay, so quickly we extend the notion of the norm, and that will open up everything you think about it from calculus or any other field. So let's define it. They are all free now. You see, because you set up the foundation, so you just copy whatever you did before. This is the way you do research in mathematics. And you get the machine, the key, and then you can continue free. So the free is going to be, this is it, definition. We bring the norm that give us a distance, and as soon as you have a distance in mathematics, you are set to go. Okay, there you are. So suppose, okay, so the distance would mean sometimes something which is different from the everyday life. So suppose V is an inner product space. When we say an inner product space, this means there is a product on it, okay? If this is going to be, say V is an inner product space, and let's say a U is going to be, or V, U is in V. Okay, this is it. Okay, then the norm of the vector U is defined by, is going to be defined by, that's it. So you want to define norm of U, just define it as usual. So what's going to be norm of U? Norm of U is going to be the dot product, U dot, okay, U dot U, but you have to take it to the 1/2. Okay, or just, or just the usual definition is going to be the square root of, okay, the square root of U dot U. Sorry, not U dot U, just the product. Okay, this is it. Okay, we know that this number is non-negative because this is one of the properties that we have. Okay, this is going to be one property that we have. So since it's a non-negative number, so what we can do is we can, okay, we can take the square root of this number. So we take the square root, and this is going to be the norm of the vector V. Okay, so it depends what vector space do you have. Then you can, you can find the norm for us to get these numbers. Okay, so this is going to be a norm. So quickly, as soon as you get the distance, then you can define. Okay, so the particular case is if you get the Rn and the usual one, that was a distance from the origin. So now we can do is more that we can do is also if U and V are going to be two vectors, are vectors, okay, vectors in V, then the distance, okay, then the distance between U and V, okay, is denoted, okay, denoted by the distance d of U comma V, and is defined by, is going to be defined by what? Just the norm. Okay, is going to be the norm of the U this is it. It's going to be, yes, the norm of u minus v. You know that this negative sign means it's okay because you're working with the vector space. So you're working with the vector space. So what you do, is just the usual procedure, the usual things that you did, okay, you did before, and simply you just using it, okay, you're just using these terms again, okay. So as soon as you define your norm, then you'll be able to define your distance formula. So in practice, this V, the inner product space, with this norm that you define, we are going to call it a norm space in general. Okay, so they say it's going to be a norm space. Then you can easily now prove that the property that a distance should have. Okay, so it can be proved, or it can be seen that, you see, note that when you say distance, the distance should have the following property. What is the first property of a distance? The property of the distance is going to be, you know, that the distance between two vectors, distance between here and San Diego, it must be always a non-negative number. Okay, it's non-negative because you define by a norm, and the norm is here. Okay, so a distance is going to be non-negative. The other one is the distance is symmetric. So this means, the distance from here to San Diego is 35 miles, and the distance from San Diego to here is 35 miles. So a distance between u and v is the same as the distance of the v and the u. See, again, this is the norm, this is the dot inner product, so we get it right away. Okay, what's going to be the other one? The other one is going to be, this can be proved later, and we already know it, that if you want to go from here to San Diego, okay, so if you go somewhere else first, then go to the San Diego, so you are not going to have a shortest distance. The shortest distance is just keep going on the straight line. But if you don't go in the straight line, so this is going to be less than equal to the, okay, if you go to the, okay, you stop somewhere like W, and then from W, you just keep going to the San Diego. Okay, so this means if you have, you see, if this is going to be U, and this is going to be V. If you want to go from U to V, okay, this is the shortest distance. But if you go somewhere else, okay, if you want to go somewhere else and then come back, you know that your distance is going to be, the shortest distance if you go along this straight line. If you switch it, it's going to be higher. They call it triangle inequality. This one, you know that in each triangle, the length of each side is going to be less than the sum of the other two. Okay, so this give you, or there is something else we can talk about it here. Like that was the fourth one. If a distance between 2 points happen to be equal to 0, if your distance is 0, means you didn't move. So this is going to be the case that the u is equal to the v. Okay, it's great formula. If you want to continue to get to the advanced mathematics or physics or whatever you like, you see, if you have a space, if you have a vector space, and on that vector space, you can define this d function, the distance function. This is called a metric. It's called a metric. And if you have a space with the definition of a distance, this space is called a metric space. So this is, when you're dealing with the inner product, that's nice. You get it all the time, but you don't need these. There are two directions later on in mathematics. One direction, you stay with the inner product space and you keep going. The other direction is all abstracts. This type of the inner product space, eventually in infinite dimensional, would end up with a class of spaces that we call it Hilbert spaces. Hilbert Okay, great German mathematician. Okay, Hilbert spaces. The Hilbert spaces, the basic is this inner product space that we're going to do it. But if you follow this norm, but you didn't go through the inner product space, you can do most of these, most of them. But the thing's a little bit more complicated. In that case, you end up with a space that we call it Banach space or Banach space. Great Polish mathematicians. So mathematics would be divided in two parts. If you want to suffer, Banach spaces. If you want to be relaxed, Hilbert spaces. So everything you do in science, in physics, quantum mechanics, you are here because you use the inner product space. But if you are a math major, you are here because in math major, you are prepared to do more job. Banach spaces and the Hilbert spaces. Hilbert spaces, in any Hilbert space, there is an inner product. All the examples that I gave you would end up into the, in infinite dimensional, would end up with the Hilbert space, which is a great, great part of the linear algebra. Okay, and so just step by step, we're just taking to this, okay, the idea of the norm. Then you see, we can go on. We can go on and prove. Remember Cauchy-Schwarz inequality, parallelogram identity, all those type that we talked about it before. We can do it. I'll just give you one more example. I just leave it here. This is 6.1. Just check a couple of examples. I will assign a couple of problems at this section. We just put these together. So we get to the distance formula. Then we are going to review really what we did with the inner product space. Those definition inequalities in case of the norm, we are very much interested in the orthogonality, okay? So where two vectors are going to be perpendicular to each other. That's the main part we are interested in. Then I do that one later, okay? So just give you one example. Just don't be surprised if you've been asked to do this type of problems. You have it in your assignment. Okay, so study this carefully to understand it. And this is science. If you want to continue to do anything in postgraduate level, okay, you have to go through this type of ideas. Mathematics is the extension of the inner product, inner product space. As I told you, those two type of spaces that we have. Okay, so don't be surprised if you've been asked this type of question. Okay, so you may be given two functions. Okay, so this example going to be one. Okay, so what we would like to do is consider, okay, the vector space of all continuous function on 0, 1. Okay, you must know quickly what we are talking about. Okay, consider this is going to be the vector space. The vector space of all continuous function. Continuous function. I say with the standard. With the standard inner product. You must know it yourself. And we say in standard, you know that this is going to be the inner product of f and g. In this case, going to be integral from 0 to 1, f of x, gx, dx. Okay, so that's what we mean by the standard. Okay, so that would be given to you, and we want to find what is determine. We want to determine the norm of. Okay, determine the norm of the function. Okay, the function is f of x equal to Okay, the function is going to be f of x equal to the 5x squared plus 1. Okay, so this is going to be the case that a little bit of calculus, not much, but we have to go through these classic examples. So we may ask you, okay, solution, definition of the norm. Okay, you know that this is it. So the norm of f. You can go with the norm square as we did it before. Norm of s squared is going to be what? Is going to be the, not the dot product this time, inner product. F and f. Okay, you put it over here, which is going to be equal to, in this case, going to be integral 0 to 1, f of x squared dx. Okay, substitute, so it's going to be 0 to 1. So your function is 5x squared plus 1. Okay, all squared dx. So just, square it and integrate it. 0 to 1, square of the first one, 25x to the fourth, twice of the first times second, 210x squared plus 1 dx. Okay, I just use the square of the binomial, square of the first one, I multiply these three numbers together, 10x squared and 1. The easy integral is it's going to be 25, and this is x to the fifth over 5, and this is going to be 10x cubed over 3, and the x to be evaluated from 0 to 1. Okay, you simplify these two and then you substitute. So that gives you 5x to the fifth plus 10 third of x to the third plus x from 0 to 1. If you substitute the 1, so that gives you 5 plus 10 third, okay, plus 1. And you substitute 0, you are going to not to get anything. Okay, it's going to be minus 0 if you like. So it's going to be 6 plus 10 third, 18, 28 third. Okay, so this is a norm f squared is equal to the 28 third. So you are going to find the norm f. So the norm f is going to be the square root of 28 over 3. Okay, you can use your calculator, just leave it as is. Okay, so that give you the norm in this case. Okay, any question? So be prepared for a couple of these type of problems. You can have a similar one with the matrices that we teach. Okay, I'll just give you one more because you have similar one in your book. Okay, just make sure you know the definition and just write it down. So another example is going to be, so again, consider, okay, we would like you to consider the V to be equal to the 2 by 2 matrices. Okay, so this is going to be, that's going to be, okay, so this is the inner product space, if you like, the inner product space. Okay, inner product space of all 2 by 2 matrices. Okay, you must know that what is the norm. I just remind you that on the test we expect you to know it with, okay, if 2 matrix is given to you, UV, remember, UV is going to be the trace of transpose of one of them, doesn't matter the first one or the second one. Transpose of a U, okay, transpose of the U times V, then the trace, or the other way around, you don't mind. Okay, and what we'd like to do is we'd like you to determine, Okay, determine the norm of this matrix. U equal to, okay, 2, 1, 0, and negative 1. Okay, so just the definition of the norm again. So go with the norm of the U squared, which is going to be the product of the U and the U. And in this case, this is going to be the trace. Okay, it's going to be the trace of a matrix, U transpose times U. Okay, so find it. It's going to be the trace of the U transpose. Get the U transpose switch. So it's going to be 2, 1, 0, negative 1. This is the transpose multiplied by a matrix, which is a 2, 1 over 0 and the negative 1. Okay, get the transpose of the U times U, and you multiply to get the trace. So this is it. Multiply the row column, so that give you 4. A row column that give you 2. And over here, the row column that give us a 2. Okay, and this is going to be 1 and 1, 2. Okay, so the trace is going to be the sum of the main diagonal, 4 plus 2, which is 6. So the norm of the U squared is equal to the 6. So we pick the norm of U to be radical 6. Okay, so that gives you something easy to think about it. Okay, so this is 6.1, the definition that we are going to have for the inner product. Okay, and so we give you the quiz up to this section. Okay, then we go to the 6.2, and slowly we get the 6.3, which is a great procedure. We are interested in, okay, eventually we are interested in if this inner product space would have a basis. So we'd like to have something, we call it orthogonal basis. So orthonormal basis, we call it. It's going to be a basis whose the norm of each vector is equal to the 1, and any 2 vectors in the basis are going to be orthogonal. And that's great things, you know, it's something that it's going to be important. We'd like to end up this course with that, okay, that idea. Okay, so 6.1 is where we give you the quiz. I post a practice quiz for you, and you know, the quiz on Monday, and then we continue getting these 2 other sections. Okay, that's it. I try to, I'm busy with the finals at the university because they will finish this week. But I will put all your previous grades and points together. Don't worry. If you need anything, just email me. Okay, have a good one. Take care, and be prepared, you know, for the quiz. I post the quiz over the weekend, and as usual, it's going to be due on Monday. Okay, bye-bye.